Hi guys, the IB scientist here. I'm going to walk you through today 5 ideas to ace your chemistry IA. If you're struggling with coming up with one, or if that deadline is coming up and you need some inspo, I hope that these help you out. So I thought first of all to just chat through what makes a good chemistry IA because this is vital to know. So the first thing is having a unique research question that's going to sort of connect with you personally. I believe you get 2 points for personal engagement. So something that really resonates with you is going to come through in your write-up. The second thing is you want a research question that allows for a hypothesis where the outcome isn't 100% obvious. You don't want to ask a question where pretty much anyone with some basic knowledge about chemistry would be able to guess what's going to happen. Of course, there will be an element of educated guessing, but there should still be a bit of room for analysis, interpretation, etc. Then the third thing is you need defined variables. And I know it sounds so obvious, but you'd be surprised at how many people overlook this or leave it too late. I would almost recommend thinking about your variables at the same time as you're thinking about your research question, because ideally your variables should be mentioned by name in the research question itself. So that includes independent variable, dependent variable. They're sort of like the main ones. And then the one that sort of gets forgotten are the confounding variables. They are just as important because you need to account for them in your write-up and mention what they are and how you're going to mitigate them from getting in the way of skewing your data. So how are you going to control them? You want to make sure that that's mentioned in your IA. Next is a detailed methodology. So you want to be as detailed as possible in both your method and in your material section. So that means don't just write 5 beakers, write 5 beakers of 250 mils with an uncertainty at the end. And you can look up how to calculate an uncertainty. It's super, super easy. So yeah, make sure your materials are detailed. Your methodology is detailed. I should be able to pick up your method. I'm sure you've heard your teacher say this. I should be able to pick up your method and read it and do it exactly as you did it and come out with the same result as you did it. If you feel like you're going into so much detail and you're like, oh my God, this is like ridiculously detailed, nobody cares about this, you're probably doing it right. Like you need to be meticulous and scientists love that. So you're on the right path with that. The next thing is a thorough analysis. This one kind of speaks for itself. This is sort of like the backbone of your experiment. There's no point doing an experiment if you can't share what the results are and what they mean in a scientific context through stats and analysis. So that's definitely vital. And then one thing that people often overlook too is in the intro and in the conclusion, it's really useful and worthwhile to sort of link your research question to the wider world. So like this specific thing that I'm doing in the lab, okay, it can seem pretty mundane and like I'm just doing it to get a good grade in my chemistry IA so I can pass the IB so I can go to the university I want to go to. But in the wider world, like what I'm actually doing, what applications are there of it? How does it impact industries or how does it impact the way that we live our everyday lives? Because you can find science in every single corner of society. So that's, and you know how the IB love their, world thinking and all this bigger picture stuff. So they'll eat that up for sure. And the last thing is you need to also give a sort of fair evaluation of the limits of your experiment and of your data analysis. So you need to be able at the end, at the end of your IA say, you know what, these were the limits of the experiment. This is where maybe it wasn't so great. And this is how I would improve it if I were to do it again. And don't be disheartened if you have a lot to say in your evaluation. That's not a bad thing. You don't get marked down on your IA if your experiment doesn't work. It doesn't work like that. You get marked down if you don't analyze things properly. So don't fear, even if your method didn't really work out, even if your analysis isn't exactly showing you what you thought it would, it's still okay because you can give like a good explanation in your evaluation and that can save your marks. So let's jump right into the 5 ideas. So the first one is energy content of fuels. There's a couple of options here in terms of question you can ask. You can say as your research question, how does the type of intermolecular bonding how does the type of intermolecular bonding present in a fuel affect the enthalpy of combustion? Or you could take it in a different direction and say, how and why does the enthalpy of combustion change as the length of the carbon chain increases in a homologous series? So in this situation, you would need obviously access to a school and to the right equipment to do this experiment. But you would basically use a calorimeter to calculate the heat released from combustion of different alkanes or whatever sort of fuels you want to use. In theory, if you find a good database with information about enthalpy of combustion of different fuels, you could do this with that as well. I think it might be a bit too thin, but you can ask your teacher what they think. And this links with sort of energy efficiency of cars and other vehicles that run on fuel. Obviously, like the higher the enthalpy of combustion, that means the more energy is released. And so you have more sort of bang for your buck when it comes to that fuel. And that can have repercussions for cost savings of sort of transportation companies and things like that. The second IA idea has to do with finding the activation energy of a reaction. So this would sort of be a two-step IA, and I would recommend that this go to somebody who is sort of in higher level, who has a really good grasp on this kind of stuff, because it can get a little bit convoluted. So this question is, how does increasing temperature affect the rate of reaction for a given reaction? So I left that blank, but you would probably insert the reaction that you're concerned with there. So you would basically take a reaction and calculate the rate at which it happens under different temperatures. And then what you would do is plot a graph where one axis is 1 divided by the temperature against the log of the rate constant K. And as you guys know, the rate constant K is you can only determine it experimentally. So you would also have to show calculations for that. And then you use the gradient of this graph to find the activation energy. If you really want to take this a step further, you can also try this experiment with catalyzed and uncatalyzed reactions and compare the two, compare how the rate changes for the two of them. This has very interesting links with agricultural processes that rely on fertilizer. So recently, like urea has overtaken the regular nitrogen fertilizer as the choice on farms. And urea breaks down into ammonia and carbon dioxide. This process is catalyzed by the enzyme urease, which is in the soil. And so you could potentially compare how much having urease in the soil decreases the activation energy of this reaction breaking down urea into ammonia, for example. And then similarly to the car thing, in the previous example, like talk about the sort of cost savings of having like healthy urease amounts in your soil if you're a farmer. All right, on to number 3, the amount of iron in iron tablets. Now, while the other one was pretty long and convoluted and had several steps to it, this one's a bit more simple. So if you're taking chemistry SL maybe, and it's maybe not your strongest suit, and maybe it's your only science, that kind of thing, this could be a good option for you. So in this case, you're looking at which brand of iron tablet has the highest amount of iron. And it's a simple titration experiment where you would basically take the same mass of different brands of iron tablet, crush them, put them into, water, make a solution, and then do a titration experiment using potassium manganate to find the concentration of iron in your solution. Once you have the concentration of iron in your solution, you can figure out basically the mass and like the percentage mass of pure iron in each brand's tablet. If you really want to take this a step further, you can compare it to the amount shown on the box and see how that stacks up. You can also compare the experimental amount that you got with the theoretical amount based off of the information on the box of the iron tablet that you're using, and see how those things vary. This obviously has links with human health and biochemistry. Everybody sort of needs iron in their body, and a lot of people are iron deficient, so take iron tablets regularly. So you can sort of dive into that and discuss what the implications are of these different brands on human health. The fourth option is vitamin C in food. Now, this one I feel like is probably the most common IA question that I get DM'd on my Instagram page. You should check it out. It's the IB Scientist. And I think it's easy to feel like this one's been beaten to death, but there's always a new way to look at things. There's always a new perspective you can take. So this one is the cooking time and how it affects vitamin C levels. So how does cooking time affect the amount of vitamin C in, let's say, 100 grams of fresh oranges? Now, you could do this on any food that you wanted, any fruit or vegetable that you wanted. It doesn't have to be 100 grams. That's just what I put in this question. So what you would basically do is you would take the amount of fruit that you decided on and you would cook it for various lengths of time. So you would take, in this case, 5 times 100 grams of oranges, and the first 100 grams you wouldn't cook. You'd cook for 0 minutes. So that means you would just test it raw. The second one you would cook for 5 minutes, then the third batch you would cook for 10 minutes, then for 15 minutes, and for 20 minutes. And you would take the end products of those batches and titrate them all against iodine solution, which will oxidize the vitamin C, and you'll be able to see the end point of the reaction. Obviously, you need to do a bit of research into how to actually do that titration, but it shouldn't be too difficult. It's pretty straightforward. If you want to, you can also vary the cooking method rather than cooking time. Or you could look at sort of like oranges with pulp or without pulp and see how that changes things too. Like the variables are up to you to play with. Then these obviously have links also with human health, with nutrition, and I put here the marmalade industry with a question mark because I feel like, I don't know, maybe fresh oranges versus orange juice versus orange marmalade, maybe there's different levels of vitamin C. I don't know. Feel free to get creative with that one. And then the final one is for my database people, my people who can't get into school to do an experiment. We're looking out for you too. So trends in bond enthalpy is definitely an IA topic that you can cover with a good database. And you can actually do a few interesting things with it. You can look at how does the bond enthalpy for a CH bond, let's say, vary as the length of an alkane increases. So you guys will know that alkanes are literally only made up of CH and CC bonds. So what you could do is you could take the total enthalpy of an alkane, which you can find in your database, subtract the average bond enthalpy of a CC bond for however many CC bonds you have in there, and then find the average bond enthalpy for the CH bond and see how those vary according to the different alkane lengths. If you don't want to do alkane lengths, the second bullet point here illustrates you can do how the CH bond strength varies depending on how branched the alkane is. So that would basically mean you take a alkane with, let's say, 6 carbons, like hexane. Hexane is a straight line of carbons, basically, 6 carbons. Then 2-methylpentane is also 6 carbons, but only 5 in a row with 1 carbon branching off. Then similarly, 2,4-dimethylbutane is also 6 carbons, but it's only 4 carbons in a row and with 2 branching off. So you can sort of ask yourself, if this alkane gets increasingly branched, how does the bond enthalpy change? This also, like the first point, relies on enthalpy of combustion, and you can sort of calculate that and plot it against the number of CH bonds and see how that changes. This has links with fire safety and industry, because if you're using alkanes for something and you don't have to use a specific alkane, you would want to be sure to use one where the enthalpy of combustion isn't crazy high, because then that could lead to unnecessary like fire hazards and things like that. So I hope you guys enjoyed. Thank you so much for watching. I hope you got some inspiration, some motivation for your chem IAs, and yeah, I wish you all best luck.
Julia, that was amazing. Guys, go ahead and drop some love for Julia in the comments. We really, really appreciate Julia coming on this channel and giving us, so much inspiration for our chem IA. It's phenomenal quality content. Now guys, also don't forget to subscribe to my channel and my Instagram at IBLikeCole, because I drop some really cool IB content. Alright, thank you guys so much. See you next time.